All right, ladies and gentlemen, we're going to talk about ideal gases with the ideal gas law. So first thing we need to do is, what do we mean by an ideal gas? An ideal gas is basically a molecule that's a gas, and it doesn't react with other gases. What we mean using kinetic molecular theory, or KMT, is that these gas particles are very tiny, that we really can't see them. The volume of the gas particles are very small compared to the container. That's going to be very important in a little bit. Gas particles collide elastically. It means they don't react. When they hit another gas particle, they rebound. All they do is transfer energy. So this is going to be the transfer of energy. Transfer of energy only, no matter. And therefore, the gas particles will not react. And this is going to be for this equation I'm going to show you about. So what we're going to do is put all these relationships that we learned in the last last lecture together. PV equals nRT, PV equal K. So if we look at this, we got P and V is equal to constant. Remember, P is equal to T and P is equal to N times K, and volume is equal to N times K, and volume is equal to N times T. All these relationships, when we put them all together, we got PV equals nRT. R is going to be the universal gas constant, and that number is 0.0812 liters, 0821, excuse me, I meant to, there we go, atmosphere times liter over Kelvin mole. So what we need to do with this ideal gas law, everything must be in atmosphere, liters, Kelvin, and mole for this to work. Now, this universal gas constant is going to be used also in thermodynamics. This is how universal it is. And so how do we got that number, the 0.0821? So when we look at gas calculations, we actually set up where temperature and pressure is going to be a standard. And for gases, this is for gases only. Temperatures at 273 Kelvin or 0 degrees Celsius. This is for gases only. Pressure is 1 atmosphere or 760 torr in port. So with these two constant, that means pressure and volume are going to change. So when we look at standard temperature and pressure, we notice that 1 mole of gas, of any gas that we consider ideal, is 22.4 liters. So we measured this, and then we came up with this gas constant is 0.0821 liters atmosphere times mole Kelvin. So we actually did this calculation. We did for all sorts of gases that we know. That's probably about 6 or 7. And within the first approximation, or the third decimal place, significant figure, everything was all the digits were the same. So we realized that our universal gas constant is this number. So for any mole of gas, of any gas, if it's at standard temperature and pressure, is going to equal 22.4 liters. This is important. This does not change either. So for standard temperature and pressure, 1 mole of gas has a volume of 22.4 liters. And so we're going to use in some of our examples later. Now we want to talk about real gases. Now, real gas is what actually happens, and all gases are actually real gases. Only during a certain temperature range and pressure range do these gases act ideal. But once we get out of that range, under ultra high pressure or very low temperatures, they do something different. And this is what you need to realize. So what happens when we keep the volume constant, but we do have these gases under extreme pressure or extreme volume? So let's look at our phase diagram. This is basically copied from the freshman level or sophomore level chemistry. If we have a gas and we decrease the temperature, we're going to end up being into a solid, keeping the temperature constant. So let's go. Let me change the color to not yellow. Oh, the yellow. So if we here and we increase the temperature up, pressure up, gas goes to a solid. So what we're seeing is that we're having some interactions occur under very high pressure or very low temperature. and we've got to do some correction factors. So let's look at these correction factors. So the first one is that the actual pressure that we see, ideal pressure, is actually a combination of the observed pressure plus this correction factor, where A is the correction factor, N squared, N is moles, V is volume. So we're taking account of any interactions that the gases may actually have. For example, if the gas is polar, you're going to see an interaction between the two molecules. This is how these things become a gas. This is what we call van der Waals interactions. Now, van der Waals interaction is actually instantaneous dipole, instantaneous dipole. So we have this type of interaction between two atoms of the same molecule, and so what's going to happen is that as the temperature goes down, they're going to slow down. Or the pressure gets high enough, the molecules are not going to see other molecules, and they're going to have this attraction because they're actually going to be close enough for a longer period of time that the electrons can actually move around and form an instantaneous dipole, which attracts other molecules. And so under very, very high pressure, what we actually see is the effect of attraction or interactions of these two of real gas. Then the second correction volume is for volume. So as we lower the temperature, our actual volume that the gases can belong cannot be any less than our correction factor, the number of moles of gas, and the actual size of the gas molecules. And so the actual volume is that the gas is in is actually a lot less in our container. So if you have this 1 liter of gas and you cool it down, what we're going to see is an increase in pressure because the gases are not moving that much, and they actually hit the surface a lot more than they do at higher temperatures. So we actually end up with this change in increase in gas. And so what we have is van der Waals equation, and this is it, where pressure is equal to nRT over V minus NB, which is correction for volume, and here's the correction for pressure at this point right here. And A and B are corrective terms that you'll get a table of, and that table will be given to you. Now, this is what we're talking about, van der Waals equations. You're going to get another video with examples of how to do both these two equations, ideal gas law and van der Waals equation. Thank you for listening. Hope you take a lot of notes. Thank you.